Good morning. Today we continue our discussion on experimental tools and techniques which one uses in the study of physical metallurgy. Last class we looked at thermal analysis in detail. We also looked at several metallographic techniques which are used to examine microstructures of metals, namely optical microscope, transmission electron microscope, scanning electron microscope. We also talked about X-ray diffraction, and to recapitulate, this concept of X-ray diffraction, maybe we look at it little again, because we have talked about stereographic projections, and I can show you with one example how you can understand or interpret X-ray diffraction or electron diffraction pattern with the help of stereographic projections. Now, X-ray diffractions or diffraction of any electromagnetic wave is guided by Bragg's law, and which is stated as 2 d sin theta equal to n lambda. Now, here theta is the angle of incident beam on a reflecting plane. This is the incident beam, this is the angle. Now, this is the transmitted beam, and the reflected beam or diffracted beam also will subtend an angle theta, and this is the normal to the beam, and this angle is 90 minus theta. So, same thing you can represent it on a stereographic projections. This is the reference sphere, projection of that reference sphere. Let us say this is the incident beam, the transmitted beam is 180 degree to this. So, basically this is the transmitted beam. Now, the angle between the incident beam and normal to the reflecting plane, this is 90 minus theta. So, what you can do, you can on this great circle 90 minus theta and draw a latitude. So, a small circle, every point on this subtends angle 90 minus theta. Now, when you use powder diffraction pattern where lambda is fixed, but you have large number of crystals. So, at least every place there is, since there are large number of crystals, there are large number of this reflecting planes. So, there will be planes at every point of this, and this will satisfy the Bragg law, and the diffracted beam you can see it subtends an angle 90 minus theta with the plane normal. So, here you check up, this is the 90. Now, draw this, or one can also argue that this angle is 2 theta with transmitted beam. So, you can mark this. So, this is this small circle represents the diffracted beam. So, basically every point you will have a diffracted beam. So, basically it will come out as a cone. So, if you put a diffractometer sensor, will sense it whenever it is located here. Similarly, if it moves along this plane, when it goes to the other half, it will again record that. Same way, it is also possible to interpret single crystal diffraction pattern. Now, usually in single crystal diffraction pattern, what you have theta is fixed because it is a single crystal, and I leave this to you as an exercise to interpret where a particular diffraction pattern from say in an FCC crystal, FCC single crystal, where will the diffraction spots from plane 1 1 1 will be located in case of a Laue diffraction pattern. We also looked at electron diffraction, since this electron also has a wave character. When it passes through a sample, some of the beams will get diffracted. Here also it will exactly follow the same diffraction principle, and you can orient the crystal, because in the electron transmission electron microscope you can tilt the specimen and you can always bring the sample to a position where you get a diffraction pattern. And if it is a single crystal, in that case here you will get pattern like this spot pattern. If these crystals are very fine, say something typically represented here, then here also you will get continuous ring. It is exactly similar to that of an X-ray diffraction pattern. In fact, these electron microscopes are indeed very powerful. Not only it helps you to look at microstructures at a very high magnifications with high resolution, but it also helps you identify precipitates from this, or precipitates or some phases which you see in the microstructure by analyzing the diffraction pattern. And also when electron beam strikes the sample, number of secondary electrons come out. They come out from different cells, and if you can measure this energy, which also can be done, in that case it is possible to find out elemental analysis of the area from where the beam is coming out. So, most of these microscopes these days, whether it is scanning electron microscope or transmission electron microscope, they are equipped with sensors which can detect or which can measure or which can identify the characteristic beams which are getting emitted from the sample, and from the intensity of these characteristic beams it is possible to do micro analysis as well. With this recapitulation, let us now move over to look at mechanical properties of metals primarily, and as has been mentioned, it is the mechanical properties which is most sensitive to microstructure. And before we look at how the microstructures can be modified to change the mechanical property, it will be good to look at some of the experimental techniques to measure different mechanical properties. In metallurgical engineering, we often talk about several mechanical properties which are listed here. This list is by no means complete, there are a few others, but in our discussion we will very often talk about these mechanical properties, primarily tensile strength, ductility, formability. We will talk about hardness, we will talk about impact strength, we will talk about fatigue and creep. Now, let us look at tensile test in little more detail. How do you perform a tensile test? For this you need a specimen which is shown over here, a typical shape of a specimen. So, this is the gauge length portion of the specimen which has uniform diameter or uniform dimensions, width and thickness if it is flat. If it is round, it has uniform diameter, and on this uniform diameter we usually mark gauge length using a marker, and distance between the two marker we say is the initial length L0, and there is a head portion in the specimen. Usually this is provided because this area is larger, and when we do tensile test we do not want fracture to take place here, we want the fracture to take place within the gauge length. So, therefore, this portion goes into the grip of the machine, and so that it can be held tightly and it provides more area of contact as well. And also we provide, which is not shown here, a little curvature here to avoid stress concentration, so that failure does not take place here. Now, this specimen is mounted on a machine called universal testing machines, which is schematically shown over here. It has a cross head which can move along these rails or along these supports. It can move, and it can move both ways, and there is a pull rod mounted along with a load cell, which is shown in the form of a spring. So, whatever pull that is applied, you can directly, you will be able to measure the pull, that P, that is force with which the sample is pulled. And we also fix on the sample a gauge, a displacement gauge, which is fitted at the marker wherever you have put the marker, and this displacement gauge converts the displacement into volt signal, and this is sent to the recorder, and it is stored in a computer disk. Similarly, the load readings, this load cell also gives volt signal, which also can be recorded on the computer disk. And the main controller is over here. This controller, what it does, it moves, there is an actuator which can move this pull rod in a user defined way. In a tensile test, we will be pulling it along this directions. So, once this is fed, once this sample is fixed into the grips, we start the machine, and this force increases with time, and we record this force against displacement. So, this plot we called load displacement plot, and this can be converted into stress strain plot. Stress is defined as force over original area. Cross sectional area is measured before you start the test. A0 is the initial cross sectional area. So, engineering stress is defined as load or pull divided by initial cross sectional area, and the strain is defined as change in length. If you define this, divide this change in length by the original change in length or original length, you get strain. Likewise, there will be a relationship between the area and strain, and usually it is the reduction in area over original area. This also is strain. Now, let us look at what information do we get from engineering stress strain diagram. We just looked at how you can convert load displacement plot into engineering stress versus engineering strain plot. Now, this has from several properties can be determined from this particular plot. So, for example, if you look at this part which is nearly linear, if you draw a line, the slope of this line which is linear, this will give you the elastic modulus. So, basically here stress is proportional, directly proportional to strain, and this is called Young's modulus or elastic modulus, and this is deformation, and this part of the plot is reversible. And we also get a stress here, there is a point from where it starts deviating from linearity. We call this proportional limit. This also one can say is a measure of yield point. And now, if we look at the maximum, so there is a point which gives you the maximum load or maximum stress the sample can withstand. So, here this is called ultimate tensile strength. what happens beyond this? The load comes down, or stress comes down. This is primarily because we are calculating stress based on the original cross sectional area. What happens beyond this point? There will be local deformation called necking, which is shown over here. There is a local deformation, there is certain area at the maybe if in a good well done test, you will get somewhere in between and at the midpoint of that gauge length, a necking will start, and this is called tensile instability. And once this stress comes down, this engineering stress keeps coming down, but truly if we find out the neck area, possibly the stress will still go on increasing. And once it fractures, there will be some relaxation, that elastic part of the stress which is reversible, that is eliminated. So, that means you move like this, and if you measure this distance or this strain, and we call this strain as ductility or elongation. This is a measure of ductility, we call it elongation. Change in length, that is a fracture, length at fracture minus original length, and you divide this difference, change in length over original length, will give you percent elongation at rupture. And very often these curves for many engineering material, they are very smooth, and it is often very difficult, and it becomes little subjective to find out the proper yield strength. So, here it is customary to define yield stress as 0.2% strain, stress at 0.2% stress. So, at 0.2% you draw a line parallel to this elastic portion of the plot, it intersects this curve here, and we call this 0.2% proof test. So, therefore, tensile test, it is a versatile test, and you get a number from tensile plot, you get a large number of properties. You get ultimate tensile strength, you get yield strength, you get Young's modulus, you get percentage elongation, proportional limit, reduction in area. You can also get calculate the area under the curve, entire curve. So, this you can say this is the energy absorbed by the material in causing fracture. So, this is a measure of toughness. Let us look at some of the typical stress strain plot of engineering materials having widely different characteristic. One is ductile, which is shown over here. It is associated with a very large deformation, and schematically how the sample dimension changes is shown here. There is a large deformation, there is a pronounced necking, and the fracture, nature of the fracture is called a cup and cone type of fracture. So, you can calculate reduction area by measuring the area over here, and change in area with respect to the original area divided by original area is the reduction in area. Whereas, in a brittle material there is little plastic deformation, it breaks as you pull within the elastic region only the fracture occurs. So, this is the fractured piece, there is hardly any sign of any deformation. Same thing is explained here, is a brittle fracture, no deformation, a ductile fracture where you have a distinctly cup and cone kind of a fracture, which is shown here, and sometime in materials, as we will know, they become embrittle, and some of these material they exhibit intergranular fracture. So, something like this, where the crack propagates along the grain boundary. Now, stress strain plot is quite sensitive to the crystal structure of material. Most materials, they are not pure, they will have some impurity. And broadly metals, majority of the metals that we use they are either face centered cubic or body centered cubic. For example, steel is a body centered cubic material. In case of a steel, which as we go along the course, we will find out, we will learn that it is not, it is an alloy of iron and carbon. Even if the purest form of iron, there will be some amount of impurity dissolved in it, and which occupy the interstitial sites, and that is why we get a characteristic stress strain plots, which is shown over here. They have prominent yield point and yield point elongations. Once it yields, I mean there is some kind of instability. This is called yield point elongation here to here, and this is called yield point phenomena. This is primarily associated with the interstitial atoms present in BCC lattice, and after this yield point, then the plot goes like this. An important thing is, if you cold work a material steel, say if you unload it from here, it will come down like this, that elastic portion of the strain, which is reversible. So, it will come down over here, there will be a permanent deformation. If you load it again, you will find that yield point phenomena is no longer there, if you load it again immediately after, and we will later on learn this in detail. Whereas, in case of a face centered cubic structure, the plot is very smooth. For example, in case of copper or aluminum, you will get a smooth stress strain plot as shown over here. Now, as has been mentioned, there is, we should make a distinction between engineering stress, and very often we talk about true stress and strain diagram. So, here engineering strain, as we have seen, is defined as change in length L minus original length, change in length with respect to the original length divided by the original length. Similarly, stress is defined as force or pull over a normal stress per unit area, and this area is the original area. As against this, it is possible to define true strain as change in length over instantaneous length. Similarly, you can define true stress as load over instantaneous area. In that case, it is possible, this is a simple mathematics. If you integrate this, you will get a relationship between true stress as true strain and engineering strain. And quickly I can show this here. Say suppose I integrate it from initial length to the final length or length at any instant, then this will be ln L over L naught. In fact, this can be written as ln L 0 plus delta L So, therefore, you can say that this is equal to delta L over original length, whereas this is the engineering strain. And I will leave it to you to convert using this type of relationship. It is possible to convert this engineering stress strain diagram into a true stress strain diagram, which is like this. So, here it does not come down. So, there will be, but when necking takes place, no longer state of stress will be uniaxial. You may have to apply certain additional corrections, but nevertheless you must realize there is a difference between true stress strain plot and engineering stress strain plot. but up to a certain amount of strain, say maybe up to say maybe 3-4% strain, the difference will be so small, it will be difficult to differentiate. Maybe in this part it will be difficult to differentiate. Now, you take this as an exercise. So, this part of this plastic portion of the stress strain plot, engineering this true stress strain plot can be represented by an expression like this. And here you try and show that here this n is a measure of uniform elongation. So, that means you get uniform elongation until this point. The uniform elongation means, as has been mentioned, this area at any instant times the length, gauge length. This relationship you can make a conversion, I mean from elongation, change in elongation can easily be converted into reduction in area. But once necking starts, you have to be careful, although there is no volume change, but this simple relationship will no longer be valid. And you try and show that this is a equal to n is equal to is a measure of uniform elongation. As a hint, I can give you that P is the load, which is given as sigma times area, and when P is maximum, so that is here the differential dP, this is 0. Now, let us look at hardness. How do you define hardness? Hardness is resistance to scratch or indentation. Now, scratch hardness is very qualitative. There is a scale called Mohs scale of hardness. It is a qualitative index, starts from 0 to 10. The talc is the softest material with Mohs hardness 0, diamond is the hardest with hardness number 10. But this is more of a qualitative index. In engineering, we use hardness, indentation, resistance to indentation as the measure of hardness. This test is very simple. Unlike tensile test, you do not have to use standard test piece, which has to be machined properly, and your dimensions have to be accurate, and surface finish has to be good. এটা আগে দেখে নিলে which 8 this 3 common hardness measuring devices which are listed here. So, Rockwell, it uses an indenter which is made of a diamond cone, or it can also have a steel ball indenter. You have a Brinell hardness tester where a steel ball indenter is used, and Vickers hardness testing machines where a diamond square base pyramid is used as an indenter. Now, let us look at the concept of Brinell hardness measurement. You have an indenter which is mounted on a small that cylinder. So, this is the indenter, and this is made up of a hardened steel ball, and this indenter is so hard that it does not deform. It has a hardness level much higher than the material on which measurement is to be taken. Then when you apply load, this indenter penetrates into the sample and leaves an impression, something like this. And if you look at it from the top, you may get a view something like this. This is the impression that you get. And now what you need to do, you measure the diameter of this indentation, and from this diameter of this indentation, that area, the contact area of that during indentation A is to be measured. And how do you do it? It can be done very easily. I will leave this as an exercise. Assume that this is the indenter, it is a spherical indenter with a diameter d, and this is the diameter of the indentation mark on the sample. And to measure this, one uses a graduated eyepiece, which has some magnifying power, and it has a graduated scale, and on the scale you can directly read this diameter, maybe in millimeter or micron, and you can show that this is a sphere, and you try to measure the surface area of the contact area along this indentation, which can be done by a simple integration, and this comes out to be this. And hardness, Brinell hardness number is defined as load over this contact area, and Brinell hardness number is not independent of load. There are guidelines for selection of load. For example, in the case of steel, you use this expression to calculate what load you need to apply. The load to be applied is equal to 30 diameter to the power 2, 30 d square. So, if the diameter of the ball indenter is 10 millimeter, then 3000 kg load must be applied to the indenter. So, therefore, you can well imagine the dimension of this indentation is quite large, and usually the Brinell hardness measurement is used on materials which has a lot of heterogeneity, something like cast iron, but you can also have Brinell hardness measurement with smaller indenter, smaller load as well. Now, Vickers hardness measurement principle is also exactly similar to that of Brinell, only difference is the type of indenter, it is different. It is indenter, it is a diamond cone with a square base pyramid. So, base of the square is something like this square base pyramid, and the angle is very specific. That angle between the two faces of the pyramid, opposite faces of the pyramid, is 136 degree, and usually the load is in this range 1 to 120 kg. So, you can well imagine the dimension of the indentation here will be very small, and you need in fact a microscope with a graduated eyepiece to measure the dimension of the indentation, which is schematically shown over here. So, once you place the load here, the indenter will penetrate into the material, and after that you withdraw the load and then bring the specimen under a microscope, which is shown here schematically, and then you sometime these days you can project it on the screen also of the microscope, and then you can measure the diagonal of the indentation mark. It is customary to measure both the diameter, this as well as both the diagonal, that is d 1 and d 2, and find out arithmetic average of the two, and then you can calculate Vickers hardness number H v using this expression. I leave it to you to derive this. It is hardness here also is exactly defined as same as Brinell hardness number, that is load over the contact area, and here theta is the apex angle 136 degree. And this hardness measurement, as has been as is apparent, is a very simple test. It does not need a very large amount of material. It can be done on a very small piece of metal, particularly this Vickers hardness, and therefore, and there is some direct relationship between Vickers hardness and the flow stress of the material, which is shown here. Sigma 0 is the flow stress, which is you can say this is some kind of an yield stress in between yield stress and UTS. So, this Vickers hardness number. So, if you measure hardness, you will get some idea about the tensile strength of the material. Now, there is also another hardness scale which engineers very commonly use, is a Rockwell hardness scale. This is also, this principle is little different. Here, you know, here that indenter is either a diamond cone indenter with an apex angle of 120 degree, and here you initially apply a minor load of around 10 kg. So, that the indenter sits on the sample, and then you apply the major load. When you apply the major load, it penetrates into the material, and what you measure the change in this depth of indentation from minor load to the major load, and this depth of indentation has some kind of an inverse relationship with hardness. That means, higher the depth of penetration or higher is the depth of indentation, lower is the hardness, and this Rockwell hardness number is something like capital D minus small d. This is some constant depending on the scale that you use, a minus d. So, it is a linear function of this depth of penetration, and depending on the choice of load and the indenter, you have hardness is measured in different scales which are listed here, like Rockwell A, Rockwell C, Rockwell B. Now, out of these, Rockwell C is most commonly used for hardened steels, and here the minor load is 10 kg, major load is 140 kg, and indenter is a diamond cone indenter with apex angle 120 degree. Whereas, for softer material, one prefers to use Rockwell B scale, and here also the minor load is still 10 kg, but major load is 90 kg, and a steel ball indenter is used with a diameter 1/16 of an inch. Now, irrespective of whichever unit or whichever machine in use for hardness measurement, there are nowadays conversion tables are available, and you can convert the hardness measurement from one scale to another. And many of these modern testing machines, they come with a loaded software which does this conversion automatically. Now, let us look at, we have looked at tensile test, and tensile test load is applied gradually. Now, what happens to a material if the load is applied at a very high strain rate? Say, suppose you something like a hammering, then is it still ductile? Now, we find that particularly BCC metals, it is highly sensitive to the strain rate of testing. So, particularly for steel, a test method has been devised which is called impact testing, and let us look at impact testing. This is a typical impact testing machine which is schematically shown. Now, question comes up, what is impact property? It is the ability of the material to withstand crack nucleation and growth under shock loading or impact loading. What we do here, we use a specimen something or a standard test piece which is shown over here. So, this has a square cross section 10 by 10 millimeter cross section, 55 millimeter long, and on this we make a V notch, V groove, V notch. This angle is 45 degree and the notch depth is 2 millimeter. And what we do, we place this standard notch specimen over here and strike it with a hammer which is attached to a pendulum, which is shown over here, and this hammer will strike the test piece in this phase opposite the V notch, and we try to measure that energy that is required to cause fracture in this notched test piece, and this value is called Charpy impact value, which is, and what we do is that there is a little animation, and this impact testing device, there is a pendulum kind of arrangement. This is a rod on which a massive hammer is attached. This is the head of the hammer which strikes the test piece at this particular point. Now, you raise it to a particular level, there will be an indicator, usually there is a pointer which indicates that height up to which it has been raised, and then you place the sample here at the base horizontally, and then so this is the sample which is placed horizontally, and thus you release this hammer. This height is measured, you release the hammer, the sample fractures, it falls off, then you measure this height, and after it goes to the other side the pendulum, it will come back to its initial position, and this takes hardly a fraction of second for the test to conduct. And what you do is you convert this height into energy. The mass of the hammer is known. So, mg times this h1, this height minus this height will give you the Charpy V notch value. So, this is a measure of the energy that is needed to rupture or fracture the test piece. And usually it is better to calculate it, this gives a little better method of finding out this height. What you do is you find out, you first do not keep a specimen, release the hammer from a height and see to what height it goes. So, this is without specimen, and then you keep the specimen and then repeat the test. So, this will possibly, by this you will be able to eliminate some of the energy loss which is absorbed by maybe improper lubrication etcetera over here. Now, steel has a very important characteristics. Many of these failures of steel structure has taken place in a brittle manner. We all know about the failure of a Titanic ship which failed when it went to a region where and it struck an iceberg. So, basically the temperature was very low. So, at low temperature steel, in many instances steel structures have failed in a brittle manner in fraction of a second, leading to lot of life, and particularly the Liberty ships during the Second World War failure has also been related to this kind of a brittle failure. Now, if you do the test at a particular temperature and then you plot that Charpy V notch value, what you get is this type of a plot. The steel undergoes a ductile to brittle transition. At a room temperature, it may show good ductility, it may have high impact value, but as you conduct the test at lower and lower temperature, you will find that Charpy V notch value goes down to a minimum value something over here, which is virtually nearly 0. So, maybe at room temperature this energy may be around 200 joule. So, at low temperature it may go down to maybe 5 or 10 joules, and this temperature is called the transition temperature, where the fracture moves over from ductile to brittle fracture. Now, the appearance of these two fractures are entirely different. The fracture at room temperature in steel is fibrous. It is associated with a large plastic deformation. You can see with the naked eye the notch root contraction, whereas at a low temperature fracture occurs with very little notch root contraction, and this type of fracture is called cleavage or granular fracture. And typical surface of the fracture which is shown here, this is the typical appearance of the fracture, and particularly look at this. There is a large deformations around this, around that notch root. There is a large deformation, so which is a sign of plastic deformation and ductile fracture. Now, let us look at fatigue property. Now, any component when it is subjected to cyclic loading, it is subjected to fatigue. Something like aircraft, when it flies at a height say 30,000 feet or higher, there the inside the fuselage has to be pressurized. So, every time the aircraft goes up, it acts as a pressure vessel, but when it comes down, the pressure outside and inside is same. So, similarly think about a wheel, a rail of a car or of a railway carriage, wheel or rail. So, basically these components, they are subjected to cyclic loading. Stress at a point keeps on varying, it is not subjected to a constant stress, which is pictorially which is shown over here. So, any component, the stress, if it keeps on fluctuating something like this, it goes to a maximum stress, then goes to a minimum stress. It can be tension, it can be tension, compression, and diagrammatically which is shown here. So, when you subject to such a loading, so the sample will keep on fluctuating, that means strain at a particular point, once it will increase, decrease, and as a result the crack will nucleate at a certain point, and then it will propagate through, leading to fracture. And this can take place, fracture in such case can take place at a stress level much lower than the yield strength of the material. And to find out the resistance to fatigue, kind of a loading, such cyclic loading, a simplest test is a rotating beam fatigue testing, and which is done machines are available, which is diagram schematically shown here. There is a motor on which a standard test piece is mounted. Test piece is something like this. It has a reduced section over here. This is primarily because it is loaded like a cantilever. So, reduction in this section size is designed in such a way that you have maximum stress over here. So, when failure takes place, it will take place at this particular place, and this is how the test is done. You can mount usually on the, you can mount two samples simultaneously, and this is the load which is given, and the stress on this particular sample as it rotates a particular point, let us say outer point. When it is here up, then it is in tension. When as it rotates, when it goes down, it is subjected to compression. So, this point is subjected to a stress something like this. And what you do is you try to find out how many cycles this sample takes for failure to takes place. When the sample fails, this load will fall on a micro switch here, and then this will stop the machine. You can note down the counter reading, and then this test can be done as if at different level of stress range. Stress range is defined as this maximum stress minus minimum stress, and if this test is done at different stress range, and then you plot number of cycle it withstands in x axis, and y axis you plot the stress range. Then you get a plot like this. If it is a BCC metal, say like steel, you get a plot like this. So, it has a certain limit which is called endurance limit. So, beyond at stress range below this, it has infinite fatigue life, whereas aluminum, copper, they will have plot like this. They may not have a definite endurance limit. And appearance of this fracture, it has a very typical appearance. It starts with a nucleation and it propagates slowly, which is shown here. It starts at this point, and you can often see these marks as a striation marks, and later on when this area, remaining area, becomes very less, not able to sustain this load, then this ductile fracture takes place. Now, let us look at creep property. If a material strength is a function of temperature, if a material is subjected to load at a high temperature, even if the load is much lower than this yield load, it continues to deform. This slow time dependent deformation is known as creep, and it usually this strain is measurable if the temperature is greater than 0.4 to 0.5 of melting point of the metal, where this is Tm is the melting point in degree absolute. And this is done by loading a sample in tension. There is a lever kind of arrangement. This is the sample. You can fix some extension gauge here and measure the change in length of this test piece, and you can apply the load through the lever. It needs a very precision temperature control. So, this is the furnace, and if you measure this strain and plot this strain as a function of time, you get a plot like this. There are 3 distinct stages. This is stage 1, stage 2, stage 3. This is the stage where strain rate goes on decreasing. Then you have a region where strain rate is nearly constant, and before failure takes place, there is a local deformation taking place and strain rate goes on increasing and leading to failure at this particular point. So, creep test can last for a very long duration, and it is an important property for any material which is to be used at high temperature. For example, any boiler component, superheater tubes, or a steam turbine blades, aerogas turbine blades. So, wherever these materials are subjected to high temperature, it is important to know creep properties. But problem is, to ensure life of a power plant, we have to ensure that the component lasts for several thousands of hours. So, maybe 25 years or so. So, to generate this kind of a property, the tests that you need to do are very long term tests. So, you need a little sophisticated equipment with precision temperature control, uninterrupted power supply, precision strain measurement system. And typical nature of stress versus strain versus time or creep plots are shown here. This shows the effect of stress. You increase the stress, it fails at a shorter time. This is the fracture time to fracture. You increase the temperature, then also with increasing temperature rupture time goes down. So, that means it is a strong function of stress and temperature. And since monitoring strain over a very long period is often difficult, so for engineers it is often good enough if we know the time to rupture, and which is shown that time to rupture can be determined with a little less sophisticated equipment. You do not need to measure the strain, and this rupture time also is a strong function of temperature and stress, which is shown over here. And it is quite easy to show that if you plot this against a combined time temperature parameter, this type parameter is known as Larsen-Miller parameter, you get a master rupture plot, and this type of plot is very helpful because you do not want to do a very long term test. So, normally if a material is to be used, let us say at 600 degrees centigrade, maybe you will do an accelerated test at 650, and then you find out time to rupture, and from that, using these kinds of a master rupture plot, it is possible to estimate the likely design life of the material. With this, we come to the end of this topic on experimental tools and techniques. And what we learned in this course is basically the metallographic techniques to look at the microstructure. We looked at X-ray diffraction technique to identify phases. We looked at mechanical properties, and also we looked at thermal analysis, which helps us to know the transformation temperatures in materials. And with this, we finish the second chapter, and in the next class, we will look at evolution of structures in pure metals. Thank you.